Bismillahirrahmanirrahim. Today we start our next lecture. There is a definition of dense subsets. What are start? Let A and B be subsets of a metric space X, D. A is said to be dense with respect to B if B is contained in the layer of A. B is contained in the layer of A. That means what is layer of A? We know that layer of A is the A and its limit point. It is the union of A and its limit point. So it means every point of B is either in A or limit point of A. Next theorem is let A be a subset of a metric space such that A is dense with respect to B and B is dense with respect to another, say C. Then A is dense with respect to C. A is dense with respect to B, then by definition B must be contained in the layer of A, so B must be contained in the layer of A, and B is dense with respect to C, so C must be contained in the layer of B. But we know that B is contained in A layer implies that B layer also contained in A layer by using 2 and 3. That means C contained in B layer and B layer is contained in A layer. So it means C contained in A layer mean that A is dense with respect to C. Let's start our next theorem, that is let A be a subsets of xt. Then the following statements about A are equivalents. Number 1, A is dense in X. Every non-empty open set in X has a non-empty intersection with A. And C is every open ball has non-empty intersection with A. To prove this theorem, we have to prove A implies. So let's start its proof. Firstly, we prove that A implies B. Suppose that what is A? A is dense in X. Suppose that A is dense in X. Then by definition, A layer must be equals to X. Let U be any non-empty open set in X, since every open point of X, as we know, every open point of X is either in A or a limit point of A. If X belongs to U, U is a subset of X. Actually, U is a subset of X. So every point of U is actually every point of X, and we know for X that either X is in A or a limit point of A. So if X is in A or is a limit point of A, so it must be contained, it must have with intersection with A is non-empty. Why? Because if X is in A, then of course its intersection is non-empty, but if its limit point, then by definition it has non-empty intersection with A. Next, B implies C. This is obvious because each open ball is open set. What is B? B is every non-empty open set in X has a non-empty intersection with A. If every open set has, so we know that every open ball has a non-empty intersection. So it means every open ball is a open set. Clear? Next, C implies A. What is C? Every open ball in X has a non-empty intersection with A. Let X belongs to X and consider a open ball B of XOR. Then B of XOR with intersection with A must be non-empty. Why? By the our supposition that every open ball has a non-empty intersection with A. So B of XOR is an open ball, so it must have non-empty intersection with A. Hence, either if it has a non-empty intersection with A, then what are the consequences? Either X belongs to A or X is a limit point of A. If X belongs to A or it's a limit point of A, so it means X belongs to A layer. What is X implies that X belongs to A layer implies that X is an arbitrary element of capital X. So it means whole X is contained in A layer, and this is the definition of dense subs. That means A is dense in X. Or a set is a dense in a space. Let A subset A of metric space is dense in X if X is equals to A layer. Okay, mean we check here. If A is dense with respect to X, then by definition X must be contained in A layer. But X being a space, A layer must be contained in X. So using 1 and 2, we get X is equals to A layer.